Okay, so today we're going to be going over some basics of enzyme kinetics to help you prepare for your final exam. So really, before we go into everything about enzyme kinetics and delving into stuff like Vmax and Km, let's review what enzymes do in a reaction. So here we have a graph of free energy plotted against a reaction progress on the x-axis. So we're looking at these curves here. The blue curve that I've drawn is supposed to symbolize the uncatalyzed reaction. So the delta G, a double dagger, the activation energy, which is the energy at this transition state here, compared to the starting energy state. So the difference between this starting point and this transition state here. So with the delta G double dagger uncatalyzed, we see that this change in energy is quite large as opposed to this red curve here where the delta G double dagger catalyzed has a lower activation energy. So with that being said, we know that our enzymes decrease the activation energy, or we can say that the enzymes decrease delta G double dagger. They're essentially making that change in the activation energy smaller. Another thing to remember from the first part of the course is that the enzymes are not consumed in reactions. So if an enzyme is consumed or used up or somehow permanently changed, it is not a true enzyme. Okay? So enzymes essentially increase the rate of converting our substrate to product by decreasing our delta G double dagger. Okay? And so when we're looking at a typical reaction, almost any reaction that has an enzyme involved, we can simplify it into this type of equation. So here we have our enzyme plus substrate, our starting units, combining to form an enzyme substrate intermediate here, and finally our enzyme plus product as the final endpoint of this reaction. And you can go back and forth between the two. That's what these double-headed arrows are supposed to mean. We also have this reaction velocity or rate of the reaction. We call that V. Okay, so reaction velocity, just velocity or rate of the reaction. How fast are you converting substrate to product? And we consider that the change in product over the change in time. And so oftentimes there is a constant of this velocity. Okay, so we call that K. So that is our essentially like our rate constant. Okay, and when we're looking at enzyme kinetics, there are a few assumptions that we really need to make. Okay, so we have to assume, number one, that the enzyme concentration is constant, right? So that means that even if we were studying enzyme kinetics, in vivo, we need to discount protein synthesis and protein degradation. So there's no change in enzyme concentration. And even if we were studying it in vitro, we need to assume that this level does not change and that, enzymes are not being denatured, right? Second thing is that we need to assume that K is constant, and K is affected by a lot of environmental factors such as temperature and pressure. So we need to assume that there's no change in these environmental factors that would cause K to change. Okay, so let's go through an example here. So let's say that we have a microcentrifuge tube, okay? And in this tube, we've only got 5 units of this enzyme here, okay? So, or not units, just we have 5 enzymes, okay? These blue guys here, these blue enzymes, all right? And we have a ton of substrate. When I say plenty of substrate, it would imply that we are saturating these enzymes here, okay? And we're also told that each enzyme here can catalyze 10 reactions per second. Okay, so this means that our maximum rate of reactions in this test tube, this microcentrifuge tube, should be 50 reactions per second because we have 5 enzymes and each of them can catalyze at 10 reactions per second, okay? However, if we were to increase the amount of substrate, if I were to add more of my red diamond substrates here, we wouldn't be able to change that Vmax because I've already told you that we're saturating our enzymes, okay? So being able to increase our reaction velocity will only work up until you hit Vmax, and we'll show you that in the next graph here. Okay, so here is a reaction velocity graph. Okay, so on the y-axis we have the velocity of the reaction velocity that I've just written here in V for short. And here we have our substrate concentration, okay? And our enzyme concentration should be maintained constant, okay? So regardless of what my substrate concentration is, like my enzyme concentration will always be maintained at a steady, however many units, 50 units, 100 units, it won't change, okay? The only thing that I'm changing as I move along this x-axis is the amount of substrate that's present in my test tube, okay? So as I'm moving along here, I can see that my reaction velocity is increasing. So let's say that I increase my substrate a little bit. Okay, so let's say I'm here, my reaction velocity would, I don't know, let's say this is 5, and I move along here, add some more substrate. Let's say my reaction velocity has now moved to 15 or something. Okay, so yes, my reaction velocity does increase, but only until Vmax is reached. After that, you're saturating your enzymes so much that they're working as hard as they can, and they can't effectively increase their velocity anymore, okay? So that's the rule to remember here, okay? So the reaction velocity will increase as the substrate concentration increases until we hit Vmax, okay? So when we're looking at the steady state assumption, there are a few rules that we need to keep in mind to understand how this assumption really works, okay? So the first thing to remember is that we're assuming that this ES complex here, this enzyme substrate sort of transition intermediate concentration, is always maintained constant, okay? So that forces us to invoke this rule that the formation of this enzyme substrate complex is going to equal the loss of the enzyme substrate complex, okay? So that would be the only way we can maintain this constant concentration of this ES intermediate here. So the reactions that are making ES would be rate 1 here and rate -2. Notice the arrowheads are both pointing in, so this means that they're both contributing to the formation of ES, okay? If we're looking at the loss, let's look at the arrowheads that point away, all right? So rate -1 and rate 2 reactions are both pointing away from ES. This means that they're both contributing to the loss of ES, okay? So this means that rate 1 plus rate 2 has to equal rate -1 and rate 2 for ES to be maintained constant, right? So that's what we have here. Rate 1 plus rate -2 is going to equal rate -1 plus rate 2, okay? So there's one caveat here that we need to kind of simplify enzyme kinetics a bit farther, and that is to ignore rate -2, okay? So we're ignoring this rate here, this green rate here. And that's because we know that enzyme plus product is going to rarely ever go back to ES. Enzyme plus product is a lot more stable than this ES intermediate here, so it's extremely unlikely and it would be considered negligible. Okay, so that makes our final equation this. So we have E plus S, forward reaction of K1, so we're just adding in our K here, okay, our rate constant, with a K -1, so that makes sense. And now we only have a single-headed arrow between ES and E plus P because we've just established the fact that it's very difficult or rare for enzyme plus product to go back to this high energy intermediate here, okay? So that's why now this is a single arrowhead with just K2. So the Michaelis constant uses these K rates that we were just looking at and defining in the previous slide to define that Michaelis constant, okay? So this is defined as K -1 plus K2 all over K1 to make this Michaelis constant. In terms of the Michaelis-Menten equation, This one is defined as V naught equals V max times substrate all over substrate plus Km. And note that this Km is that Michaelis constant that we were just talking about previously. Okay? So let's look at what Km really means and how we actually derive that 2 equal substrate concentration at half Vmax, okay? So what happens if we actually plug in Km as substrate into our Michaelis-Menten equation, okay? So we should get something that looks like this, V naught equals Vmax times substrate. So the numerator of this equation is not changing, all over 2 substrate. So that's because we put in S over here instead of Km, and that would give us 2S. And we know that we can cancel out like units in the numerator and denominator, so we cancel out our substrates, and we're left with half Vmax. And that is how we derive that Km is the substrate concentration at which reaction speed is half Vmax. Okay, so here's another graph of reaction velocity plotted against substrate. Quite similar to the one that we saw a few slides ago, but maybe with a couple added details here. So let's just review every single component of the graph again. So we have our reaction velocity here, and along the x-axis we have our substrate concentration. And remember that we have already established that as substrate increases, our velocity will increase as well until we hit Vmax, and we see this asymptoting effect. Okay? So if Vmax is defined at, let's say this is 20 here, we can move down the graph at a point that we would feel is about 50% from Vmax and define that as half Vmax. So I didn't actually draw this super accurately. Maybe this should be a little bit further down more. But half Vmax is essentially the halfway point between this Vmax and this starting initial velocity here. Okay? At that point, when you draw your dashed line over to your actual curve here and then head down to the x-axis, that is the definition of Km, okay? So at this point, we are at half Vmax velocity, so therefore our substrate concentration is defined as Km, okay? So another thing to remember is that when your substrate concentration is much, much greater than Km, so it's like off the charts here or something, extremely high substrate concentration, then, okay, your substrate concentration divided by substrate concentration plus Km, so this is part of the Michaelis-Menten equation, is going to be equal to approximately 1. So therefore, your V naught, or your velocity that you're calculating, is going to be roughly equal to Vmax, okay? Now, another thing that we can look at and identify when we're given these Kms, or when we're able to calculate these Kms, is a property of the enzyme that is affinity. So a low Km would mean that your enzyme has high affinity for its substrate, versus a high Km where your enzyme will have low affinity for the substrate, okay? So this makes sense if you kind of go back and think about it yourself. A low Km means that you don't really need a lot of substrate in that reaction tube to hit a high Vmax already, okay? Now we can also look at catalytic efficiency, okay? So to define Kcat, okay? Kcat is defined as Vmax over enzyme concentration. So this is asking how many substrate molecules can we convert to product in a unit time? And usually that is per second unit time, okay? So how quick are you to make this product from substrate? How fast are you? Okay? And if we look at catalytic efficiency, there are 2 components to this that we have already defined, okay? So Km, we've defined as how well are you able to bind to S? How high is your affinity for that, all right? And Kcat, we literally just defined a few seconds ago. Again, it's just how quick is substrate being converted to product, okay? So these 2 things, these 2 factors, the ratio of these will define how efficient you are, okay? So a highly efficient enzyme is going to have a really high Kcat over Km ratio. Because remember, you want to be able to convert substrate to products very well. Like, you want a very, very high kcat. That means that you're extremely quick at doing this reaction. And you want to have a really high affinity, which means that you would have a low Km. These two properties together would give you a highly efficient enzyme, okay? And the only thing is that there is one limiting factor. You cannot catalyze reactions faster than the diffusion rate. Enzymes can only catalyze reactions or catalyze substrates into products at the speed at which they encounter them, which is the diffusion rate or diffusion speed here, 10 to the 8 to 10 to the 9, s to the -1, m to the -1 here, okay? So I hope you found that helpful. If you have any more questions, feel free to shoot an email, and good luck on the final.